So basically what happens is, signal travels. And so there's a T, say receiver A, time at receiver B, time at receiver C. And then those times are, assuming after it's been time corrected. So after these times are measured, we take the difference between those two times, so it's time difference of arrival.
Mm-hmm.
And so that difference in time defines a hyperbola for one pair of receivers. So given all three pairs of receivers, you've got three hyperbolas intersecting. And basically, with those detection times, it goes through the position calculation, calculates the position. But what if there's a little bit of error on this receiver, a little bit of error on this receiver, and so on? So basically what happens is we inject a little bit of error in each of these detection times to see what the effect is on the calculated position. So I don't remember all the details, but basically it goes through a whole bunch of different combinations of injecting error into these detections. And for each one of those new sets of times, it calculates a new position. So basically it calculates a cloud of errored positions around it. And then just by looking at that set of errored positions, that's how HPE is calculated. So there's the HPE paper that talks about it in more detail. But basically, I believe the idea is wherever the original position is, find the position that is farthest away and use that as the measurement of error potential. Now, what you'll find is that, let's say within this receiver triangle, if you have an animal that's here, inside the triangle, the error potential is relatively small. So this error cloud will be relatively small. If the tag is here, the cloud will be much larger. Just the nature of inside the triangle, good, outside gets worse. So that could very easily account for why some fish maybe in this general area have lower HPE, whereas fish in this area have higher HPE. It's basically driven by the geometry.
So a minimum convex polygon around your total array,
right,
would kind of define
more or less. So
where you're going to get low HPE.
It depends. In the aggregate, that's generally true.
Yeah.
Assuming that tags that are inside of individual triangles are being detected by those triangles.
Right.
So for instance,
And not by only two receivers, for example.
or three receivers that aren't great.
Yeah.
So let's say you had this array here. So these four receivers, there's the minimum convex polygon. Let's say the fish is here. If it was detected by these three receivers, it would have a low HPE. If it was only detected by these three receivers, it would have a higher HPE because it's from the point of view of these receivers. And it's in a more sensitive error location for here.
Okay.
So for each basic position, so let's say it was detected by all four. So for this triangle, it will have the lowest HPE. For this triangle here, this triangle is a little bit more elongated and flat. This would probably be a bit of a higher HPE.
Yeah.
The same for this triangle. And then for this triangle here, it would have the highest HPE. So basically, we take those four basic positions, 1, 2, 3, 4, and using the individual HPE values, use those individual HPE values as the basis of the weighting. So the higher the HPE, the lower the weight. And the details on what the specific formula is are in that HPE paper.
Right. And then HPEm.
And HPEm, HPEm only exists for tags where you have a survey location. So if it's a reference tag or a sync tag, based on where the metadata said it was. Sorry.
We're getting a lecture.
No, by all means.
Based on where the metadata said, okay, let's say that there was a reference tag right here. Or this could have been another receiver with its transmitter.
Sure.
So it has the survey position that you provided using GPS. And then the positions that are calculated for this transmitter are compared against so let's say this calculated position.
Yeah.
So this calculated position is just the distance.
30
between these two.
centimeters.
Yeah.
Yeah.
So to relate HPE and HPEm, so it's not it's more of a statistical relationship here. So let me think here. HPE and HPEm. So each individual position has the HPE. Okay, sorry. For the tags where you know where they are, they'll have HPE and HPEm. So let's say for one position, there is this data point here. So this HPE and this HPEm.
So an HPE of 5 corresponds to 30 centimeters.
So basically, if you were to take all the data points and plot it on here, you generally see something like this. Something that kind of goes up like this.
Okay.
So you get a whole bunch of stuff here, a whole bunch of stuff here. And then it usually gets a little bit more sparse out here. Some of the patterns you'll see, if you just plot that data, you'll often see things that look like V's. You might see a lot of V's through the data. But the V's get wider out here and they get smaller down here.
And this plot should only be made for reference tags.
This plot should only be made for reference tags. You can do it
And
with
sync
sync
tags.
tags as well.
Yeah. But no moving tags.
Right, because we don't have the HPEm
Okay.
for the moving tags.
But you do get it in the data, right? It's just not useful.
For the animal tags?
Yeah.
Yeah, no, there's no HPEm because you need to have a known point to compare it with.
Gotcha. Okay.
Yeah, so there's not like a direct linear relationship between HPEm and HPE.
Yeah.
But if you bin this data up and calculate a statistic for each bin, like for instance, 95% of the positions in this bin are less than this. And yeah, so you can calculate a statistic for each bin, and then it's the statistic of the bin that you can use to provide a predictive model for HPE to HPEm.
For the animals.
For the animals, yeah.
Yeah. So if I said I don't want any positions with more than 5 meters of error, I could model this essentially and say, okay, my threshold is 10 meters. That corresponds to an HPE cutoff of 26.
Right. So if you want, if you want an HPEm cutoff of 10 meters, and then that corresponded to an HPE value of 26, then that's kind of how you do it.
Okay. And then you could take that to your animal data and say, we've used an HPE cutoff of 26, assuming that's about a 10 meter error. Okay, perfect. Good.
Okay.
I understand.
Okay, good.
Thank
Does
you.
it make sense to you?
It does, yeah.
Okay.
Thank you, Frank.
Well, any follow-up questions? I'd be happy to answer.